Today I want to take up the topic density of states in a band, and I'll explain in a second what I mean by that. So far what we have looked at is that there are many levels, energy levels we know in any particular band, but we want to have a feel for how many are there per unit energy, what is the distribution of these states within the band. And that's what we mean by density of states. It gives us a sense of the distribution of states within the band. So we may define the density of states as the number of states per unit energy per unit volume. Within that particular band, of course. So there's these, say, 10 to the power 22, 23 levels that we saw in the last class. So many levels are there. How are they distributed is what we'll try to go at today. Well, we can do that in different ways, but we can use some simple concepts to come up with the distribution sort of intuitively and then try to pin things down a little more mathematically. Now, if you recollect, we saw that when we look at the energy versus separation diagram, that it looked something like this. Right? This has been a long time since we did, I think. And what we see is that up to a point, as we come closer and closer, so somewhere from infinity as we bring things closer and closer to each other, the split between the levels increases. Okay? So we may put it in other words as the separation between levels is sort of inversely proportional to the interaction of atoms, or how close they are if you want. Okay? So the closer we bring them, the farther apart do these levels split. Now what we want to do is to take this idea, which is simply looking at that E versus separation curve, and to do something, namely, we'll look at a collection of atoms in a solid. And we'll focus on nearest neighbors, second nearest, and so on and so forth, and see where, when we consider a particular set of atoms, what is the kind of split between the levels. And then when we look at more and more distant neighbors as we consider the larger solid, from that we can try to intuitively guess what might be the distribution. The number of nearest neighbors is small for any given collection. The nearest neighbors will be in the range of 4 to 6, somewhere there, 4, 6, 8, like that, depending on the particular crystal structure. And then as we go farther out and we say the fourth nearest neighbor, the fifth nearest neighbor, we are talking of larger numbers of atoms involved in that, but which are farther apart. Okay? So let's look at the nearest neighbors for a second. Consider a particular plane, some arbitrary plane, and we are going to look at one atom in that plane. And I'm going to be interested in what are its nearest neighbors, and say for a particular distribution, let's say there are these 4 nearest neighbors. Remember, this is nothing mathematical, no proofs. We're just looking at trying to guess how the distribution might be. And if these are the nearest neighbors to this atom, we have 4 nearest neighbors and a collection of 5 atoms. We may draw the split in energy levels for these 5 as something like this. 5 levels are formed by this collection of 5 atoms as they are brought closer. And because they are nearest neighbors, the split is fairly large. Okay? Are you with me up to there? We've got a larger split because they are the nearest neighbors. Now as I consider atoms that are farther out, I'm going to redraw this because it's going to get a little complicated to draw it here. Then we'll find that according to our equation there, as we look at atoms that are farther out or less interactive, then we will expect that the levels will be more closely spaced together. So let's look a little farther out at, say, the second, third, and fourth nearest neighbors. And the way to do that will be, let's draw in these neighbors, and look at the, say, the third and fourth nearest neighbors and so on. The atom of interest to us is here. Okay. The one that we just looked at are these four, which we call the nearest neighbors. And then we have the second nearest neighbor atoms, which will be these atoms, which are these four. And then the third nearest that I've hatched in this way. Are you able to see? And then we have, yes or no? Yes, okay, it's come on. And then we have those third nearest, and then now we are interested in, say, the fourth nearest neighbors. So as you see, as we are going further out, we will increase in numbers. And now the fourth nearest neighbors, I got to have a way of indicating that. How about putting a minus sign through them? Okay? Those are my fourth nearest neighbors. How many fourth nearest neighbors do I have? There are 8 fourth nearest neighbors. And accordingly now, there's a larger collection of atoms that are farther apart. And so we may guess that our levels are going to be, so 9 levels that are a little more closely spaced than the previous example, 4, 5, 6, something like that, right? It's simply a guess we are doing based on our idea that as we bring them closer together, the levels split. Here they are nearest neighbors, they are farther apart. Now we've gone to something like a fourth nearest neighbor and we are farther apart. And if you extend this idea then to a solid where you've got all these atoms there, and then we think of what the distribution might look like, what would you guess? What we are looking at is the number of levels, right? Energy levels. What we have seen is that the ones farther out here will be relatively few. We're going to pack them in more towards the center because the more I add on, there'll be more and more closely spaced levels here, right? And so what we end up with is some kind of a band that looks like this. I'm going to try the band idea. Okay, there's going to be a densely packed area here and sort of fewer as we move away. Okay, because the ones out there are contributed mostly, the wider spaced ones from the nearest neighbor atoms. So if we now draw a sort of distribution, it's going to look something like this. The maximum, this is the density, coming at some energy level, and then it tapers off.
So what are we plotting the energy against?
Nothing, really, it's in space. I mean, I'm not plotting it as a function of distance as I did in the first figure, but where would the energy levels be for this collection in space? It's not as a function of distance that I'm doing here. Okay, for this, because these distances are fixed, right? So I'm not plotting it against distance. Whereas in the first curve, we were looking at as we move them closer, how it changes. So that was against distance. So this is sort of a simple, intuitive picture. Did I give you what the symbol would be for density of states? No, I didn't tell you that. Okay, we will use the symbol G as a function of E for the density of states. And this is simply from some basic ideas of what we expect it to be, and then we'll look at the mathematics of it. G of E, the function, can be defined when you multiply it with dE as the number of states. So G as a function of E times dE is the number of states in the energy interval E to E plus dE. Per unit volume. GE itself was per unit energy, per unit volume. When we multiplied it by dE, we are talking of the number of states in that interval dE, between E and E plus dE. So I can now integrate this up to a point. If you are interested to know below E dash, some energy level E dash, what is the density, the number of states per unit volume, I could then integrate it over 0 to E dash, and that term we will refer to as the volume density there. Okay, 0 to E dash. Okay? So this term here gives me the total number of states below E dash. And of course, it's per unit volume still. Okay? Now, much of this we have arrived at the distribution sort of intuitively. Now, what I want to do is, if this is true, I want to know what is this GE from which I can make use of it in calculations down the road to calculate how many electrons are there in a particular band and so on. Well, to calculate this, we need to be able to calculate this independently. Then I can, by the differential of this with respect to E, arrive at this. That's the other way of looking at it. That's a little tedious for a real solid. So what we'll do is we'll take some simplification where we'll consider the electrons in a 3D potential well, which we looked at earlier. We know its distribution of energy and so on. And we'll make that simplification that in the solid, it's going to behave, the free electrons, say the case of a metal where they're essentially free inside the solid. Okay, they are part of that gas, as we described it. And so we can use the approximation of an electron in a 3D potential well to try to arrive at this term here. And then from that to estimate what is the density of states. Well, we know for the 3D case, 3D potential well, that the energy is given by this term here, where L is the size of each side of the cube. We're considering like a cube there, or the length of each side of the cube. This is what we have for energy. And L, in this case, because it's a solid, is much larger than the atomic dimensions. I'll put the subscript M to indicate the electron. L is much larger than the lattice parameter A, because L is referring to the edges of a solid. And so what we have by consequence is that since we are dealing with such a large number, that energy levels are very closely spaced. So limiting ourselves only to free electrons in the solid, which is why we are able to use this approximation, we'll then look at arriving at the density of states. Each of these numbers, n1, n2, and n3, are integers that run from 1 upwards. Right? So what we have is now any particular combination of n1, n2, n3 refers to a particular orbital state. So we have this combination is really something n1, n2, n3, a particular orbital state it is referring to. We pin down that particular orbital state once we know these three. Okay? So for example, if n1 is 1 and n2 is 1 and n3 is say 2 or something, we will write a particular orbital state by this notation which we looked at earlier. Okay? And what we are trying to do is that for some energy E dash, we are trying to determine how many such combinations are there. And we know for each combination what will be the value of the energy. So we have some energy arbitrarily chosen, E dash, below which we are trying to determine how many combinations of n1, n2, and n3 can we have in there. Now I can rewrite that then as some maximum value will be there for this combination given by E dash by H squared. I've simply rearranged that equation in terms of the n1, n2, and n3. So this will have some maximum value based on the particular E dash that we have chosen, and we can call this maximum value N dash squared. And what we want to know is how many of these combinations are there till we reach N dash squared. Let us look at a two-dimensional picture to start with. To arrive at that number, how many combinations of N1, N2, and N3 will give us, it will be less than N dash squared. In two-dimensional space, if we plot, say, N1 on one axis and N2 on the other axis, and each of these squares then refers to a particular value of N1, N2, and so on. Okay, we give some numbers 1, 2, 3, 4, 5 for each of these 5, 6, whatever you have. And what we see immediately is that if I'm referring to a particular box like this, then that is what? Psi 2, 2. Okay, and by definition this is unit area. Each of these boxes has got some unit area in this n space. And similarly for other things. Now what I have is that if I have got n dash squared is the maximum, in this particular case because we are limiting ourselves to two dimension, my equation is simply n1 squared plus n2 squared is equal to n dash squared, which is simply the equation of what? What kind of a shape is this? It's a circle. So if I limit myself in this case to some radius n dash, we draw something like this, let us say. This is part of the circle, the quarter of the circle, which is satisfying n1 square plus n2 square is equal to n dash squared. That's the maximum that we are interested in, because all the energy, the E dash that we are interested in, all states should fall below this sum. So now I want to know how many orbital states, combinations of this, lie within this area. That's what I'm interested in. So I can determine the number of orbital states, because each of these is unit area, by knowing the area under this curve.
But then some of the states will be fractional.
Yes. It's a simplification, but if we think of each state as being one unit area, the total number of states is simply the area under the curve. Am I right? I've got X number of states, each occupying unit area, so the total area will be simply X. So if I know what is the area under this curve, I know the total number of states in this space. Okay? So we know the area under the curve is what? Pi n dash squared by 4. I've got only a quarter of that circle. So I know what is the area under this curve, which is pi n dash squared by 4, where n is simply, n dash is the radius of that curve. And from which now, knowing the area, I can say that the numbers, let me rewrite that, the number of states is equal to the area under curve, and therefore that is simply equal to pi n dash squared by 4. Okay? Now we'll use the same kind of a idea and move into 3D, where now I'll be plotting it as n1, n2, and n3. And this time again we'll have some kind of a sphere which will satisfy the equation n1 squared plus n2 squared plus n3 squared is equal to n dash squared, which was our original equation. And we are looking at only 1/8 of this sphere. Okay? So this surface here of the sphere is defined by this equation. And again the question arises, for each of the orbital states, which is now given by n1, n2, and n3, psi n1, n2, n3, each now occupying unit volume in this place. We are building it up by unit volumes. What is the total number of states below E dash will simply be given to us by the volume under this surface. Are you with me? So we know the volume is 1/8 that of the sphere. So we get 1/8 4/3 pi n dash cubed. Let me rewrite that. I write it right at the end. The volume then is 1/8 4/3 pi n dash cubed, which of course you can simplify as pi n dash cubed by 6. So these are the total number, what we may call the orbital states, that satisfy the equation n1 square plus n2 square plus n3 square is equal to n dash square. Now one more addition we can do to this is that each orbital state can occupy a maximum of how many electrons? 2, taking into account spin. So the total number, including spin, that we can have is then given to us by twice this, or simply pi by 3 n dash cubed. Okay? I can now make a substitution for n dash in terms of E dash. I want a relation in terms of energy. So what I will do is I will look for a substitution for n dash in terms of E dash. So I go back to my original equation which I had here. Namely, this equation here. N dash squared is equal to E dash by h squared 8 me L squared. So I can make the substitution here and arrive at S in terms of E dash will simply be pi L cubed by 3h cubed 8m E dash to the power 3 by 2. You can make that substitution simply for n dash from that previous equation. Now what is L cubed? Volume of the solid, right? So now when we are thinking in terms of per unit volume, I've got divided by L cubed to get pi by 3 h cubed 8 me E dash 3 by 2. So this gives me the number of states per unit volume below E dash, which if you remember is what we were looking for in order to calculate our density of states. Okay? So I got this term. Differentiating this with respect to E will give me the density of states. In other words, GE is equal to the differential of this term here with respect to E. And when you do that, we will get 8 pi 2 to the power half, or root 2, whichever way you like to express that, 3 by 2 e to the power half. Actually, it should be E dash there because we are considering only up to E dash. This part is a constant. All those are simply a bunch of constants, including the electron mass, Planck's constant, and so on. So essentially, the relationship that we have is density of states is proportional to e to the power half. So as we go from the bottom of the band, we increase in energy, the density of states increases. And if you go back and now look at the picture that we drew, more or less intuitively, what we were saying here with this picture here is that the density of states is increasing from the bottom of the band. Now we've got a function that describes this, namely this term here. It's as e to the power half. But how do we explain this portion then? Will this equation work? We have to take into account that there is some energy here at the top of the band and modify it and say it is proportional for the top of the band to E top minus E to the power half. So that as you get closer and closer to E top of the band, the density of states tends to 0. Yeah.
So in this calculation, we took into account all those squares or cubes which were not full but half.
Yeah.
So how do we account for that?
We don't. It is an approx. All this. There are many other simplifications you're making. Okay, we don't have half states. That's what you're trying to drive at, right?
Less than half.
Yeah. I mean, half means any fractional states. That's yeah. We don't, because they are integers. But this is a simplification that allows me to get some kind of a mathematical description of the distribution of electrons. Actually, we're coming to the distribution of states first, and then to the distribution of electrons. And it turns out that it's a pretty good approximation, even though there are so many simplifications to it. We know that those integers cannot be some fractions, obviously. So all the orbital states are made up of n1s, n2s, and n3s that are whole integers. So it is obvious that there is simplifications taking place here. There are lots more simplifications that will be taking place before we come at some description. But the amazing thing is that it's a pretty good fit for many cases. There are limitations on where all you can use this description, but for many cases of our interest, it's a good fit. Okay? It actually describes the behavior of the electron in the band in many cases, in reality. Okay? So the first thing here was that to account for that tapering off of density of states to the top of the band, that part is described as E top minus E. The other thing to remember is that I use the term ME, which is the electronic mass. But yesterday, or whenever it was, I think it was yesterday, last class, whenever that was, we said that there is actually an effective mass. So we should, strictly speaking, use the effective mass here, because this is the electron that is moving around inside a solid. So we have to make use of the electronic effective mass. The other thing is that we really started off with the notion that it's free electrons moving around inside the solid. That's how we started this whole business. So strictly speaking, this applies only to free electrons. But again, it turns out that it's a pretty good approximation for semiconductors and metals. When you are near band edges. So when we talk of electrons that are near the band edges in either semiconductors or metals, this description fits, even though we may not be dealing strictly with free electrons in that case. Okay. So these are some of the kind of approximations we arrive at, which give us some feel for how the density of states distribution is, mathematically speaking. Now what this told me simply is that the allowed states, where all it could possibly go, right? GE is a description of what are the allowed levels. It doesn't tell me that in the real solid where the electrons are actually sitting. So I need to have something to describe, given these allowed states and some other criteria, whatever might apply, how do the electrons decide where to go? Okay? And so we will make use of certain statistical features there. And once we know that, we will find out that we can describe that by a function f of E. This is the actual distribution of electrons. What we had was the distribution of states. So it's a probability term for where they are most likely to go into which energy levels. and then we can combine this function with the density of states function dE and integrate that to get the total number of electrons per unit volume within the band. So I integrate it over the band. So this is where we are headed. I'm just giving you a preview. We've got this term. We are going to look at this term. And once we get this term next, then we can use it to see how the electron concentration is per unit volume. To get this term, which is how do the electrons actually distribute themselves, what we have to do is to make use of statistics of collections of particles. And our particles could be anything. In this case, we are restricting ourselves to electrons. But there are statistics that applies to various collections of particles. Let us consider a collection of particles, or to begin with, let me say, what we are looking at right now is what is known as Boltzmann statistics, which you would be familiar with to some extent. Let us consider a collection of particles which are in random motion okay, and collisions are occurring. That's the picture of the gases, right? We use Boltzmann statistics very often in the kinetic theory of gases. And so this is the picture we have of the atoms in there, of the particles in there. And what we want to know is how many particles are there in the range having the energy E to E plus dE. How many of these particles per unit volume, that's always there, the concentration actually, have energies in the range E to E plus dE. We will define a term PE, which is the probability that a particle, could be an electron or something else, has an energy E. Or in other terms, it's the fraction of electrons or particles with energy E. That's an alternate. I'm not going to attempt to prove this or anything, but the distribution, it turns out, when we look at what we know of such gases particularly and so on, is that the probability is expressed in terms of A, some constant, exponential E by kT. And some of these terms come in there as sort of as best fits to the data, to the description, and where we know that K is Boltzmann's constant. Okay, he had to introduce that constant there to best explain what is observed. So the probability that the particle will have an energy E is given by this, and this PE is also then known as the Boltzmann probability function. What I can do is to sketch this energy versus the number having that energy, and because it's exponential, it will look something like this. This curve is proportional to exponential minus E by kT. So this is simply the plot of the Boltzmann exponential function. As energy increases, the number of particles having that energy decreases. Consider any two particular energies, E1 and E2, and correspondingly N2 and N1. And what we immediately have from the equation is that N2 by N1 is equal to exponential minus E2 minus E1 by KT. If E2 minus E1 is much greater than KT, what can we say about N2 with respect to N1? E2 minus E1 is much greater than KT.
N2 is much greater than N1.
N2 is much, there's a minus sign there. As this term, E2 minus E1 increases, the exponential decreases. Right? Minus. So N2 will become much smaller. Right? Which is obvious from this curve, because as we are increasing the energy, N2 is decreasing exponentially. So as long as E2 minus E1 is much greater than KT, we have N2 is much less than N1. What would happen to this distribution at any particular distribution at E2 and E1 if I increase the temperature? As T goes up, this fraction goes down, so this increases. So that means N2 increases with respect to N1 compared with some other temperature. So one way to increase this population level, the curve will look different, is increase the temperature. Then we'll have a lot more at N2 compared with N1 in the previous case. So this is nice, but can we really use it to describe the electrons within the band? Or where can we make use of Boltzmann statistics in our description of electrons? Does it really apply? Well, one, we know that the Boltzmann statistics definitely applies to gases, but what about to electrons is the question. It turns out that when we are dealing with electrons where the number of states available is much greater than the number of electrons that we are trying to put into the states, we don't have to worry too much about violating Pauli principle. There's lots of states where they can go into without violating Pauli's principle. Okay? So in that case, we can make use of Boltzmann statistics to describe the behavior of the electrons. Because there it won't violate Pauli's principle, and this description is sufficient. Where do we find such a case? In the conduction band. When electrons are there in the conduction band, remember, very few have been excited into the conduction band from the valence band. And the conduction band is practically empty. Lots and lots of states are there. So when we have such a situation with lots of available states and few electrons, then this description that makes use of Boltzmann statistics exponential E2 minus E1 by KT applies. The problem is this is not sufficient to describe all that we want to, say what about in the valence band and so on. It turns out we have available to us something else known as Fermi-Dirac statistics. And this is coming from the fact that we have the restriction of Pauli's exclusion principle. In other words, where there's lots of electrons and few states, I have to worry about this. I can't ignore this. And when I do that, then Boltzmann statistics no longer applies. The point is that we were talking of, in Boltzmann statistics, of particles that can move, collide, change their momentum and energy states, and so on. There was absolutely no restriction there on what energy states they could move to. Okay? If you want to take the picture of there's two particles that are going to come and they collide here, they started with some energy state 1, energy state 2, and when they scatter, they've gone to 3 and 4. There's absolutely, in Boltzmann statistics, no restriction on whatsoever on what values E3 and E4 can take. But after scattering, assuming that we started off with two states that are satisfying Pauli's principle, two electrons, Once they scatter, they can't take on arbitrary values because something else may be sitting at E3 and E4. So because of Pauli's principle, I have restrictions to the energy, and instead we will see that the function that will describe it is given to us by the Fermi-Dirac function. P of E was called the Boltzmann function. Similarly, F as a function of E is known as the Fermi-Dirac function, and it is the probability, similarly, of finding an electron with energy E under the circumstances that Pauli's exclusion principle and so on applies. And again, without going into great details with that, we can write Fermi's function, the Fermi-Dirac function, as 1 plus A exponential E by kT, where A is some kind of constant. It turns out that we can write A, the constant, as exponential minus EF by kT. And if that is so, then our Fermi-Dirac function then becomes 1 by 1 plus exponential E minus EF by kT, a form that you're at least familiar with, where EF is known as the Fermi energy. And when we look at this equation, which is the Fermi-Dirac function, what we see is that when E minus EF is much greater than kT, what happens to this function? When E minus EF is much greater than kT, you sure? Where? Yeah, so it's a large number, it's not, but it's not infinity. So we may approximate this by exponential minus E minus EF by kT, when E minus EF is greater than, because that was in the denominator, right? And so when it goes up into the numerator, you get the minus term. What is this? We just looked at it. Exponential minus some energy by kT. What kind of statistics was that? Boltzmann statistics, right? So what we're saying is that as long as the energies that we're talking of, E minus EF, large energies, then we can approximate even that case by Boltzmann statistics. We will see that when we plot it. And so this term, this condition here, where we have E minus EF much larger than kT, which approximates to this, is known as the Boltzmann tail. Now I'm going to plot this function in terms of energy. And it turns out that at t is equal to 0k, it's a step function. Okay? All states below, this is strictly at t is equal to 0k. All states below EF, the chances of finding an electron are 1. That means all levels up to EF are full. And everything above EF is empty. And then as we increase the temperature, we find something like this. T1 and T2, where T2 is greater than T1. And what we were talking about, the Boltzmann tail, is in fact this part of the equation, which goes higher, beyond the Fermi level. Up here, as we go higher and higher, E minus EF becomes much larger than kT, and we can approximate by Boltzmann statistics. For t greater than 0, what will we get for the Fermi-Dirac function? T greater than 0, E is equal to EF, what will happen to the Fermi-Dirac function? Half, right? And that's what has been plotted here in this figure. At T greater than 0, any temperature greater than 0 Kelvin, the probability of the electron having energy E is equal to EF is half. In fact, that will be the definition of Fermi level that we will use when we go on to describe semiconductors and things like that. If you try to think of it in terms of where there are electrons below it and above it, we will run into certain confusion when we start dealing with semiconductors with a band gap there. But when we describe it in terms of F is equal to half, the Fermi function is half when E is equal to EF, then we have the appropriate description of the Fermi energy. Not sure just how much longer I have to go. I think he's going to indicate to me, yes. Okay. Let me wrap this up with 3 figures, and we'll stop there. Just incidentally, I'll mention, it was very interesting to discover that this character, Dirac, Paul Dirac was his name, studied electrical engineering at Bristol University or somewhere there. When he was 24, he got his PhD from Cambridge, and by 31, he'd won the Nobel Prize along with Schrodinger. So what you're dealing with here is pretty complex stuff, which we've just simplified into, a few pages of notes. But this guy had to come up with all this in a very complicated fashion. Here are the 3 figures, and we'll stop there. At any temperature T greater than 0 K, we know this distribution of states looks something like this. That's my distribution of states, density of states. Correspondingly, I know that my Fermi level at some temperature is going to look like this. The Fermi function. And so what I can do is to combine these two to give me a term which I'll call n subscript E, which is the product of these two, the density of states and the Fermi function. And we'll see that initially it is this term that will dominate. So it will have the shape like this till we get to about the Fermi level. Okay? And though there are states still available there, because the Fermi function suddenly drops, so does this product. So this function here is describing the distribution of electrons. This is the density of states, how electrons like to sit at various energy levels, and then this describes to me the product of GE and FE. And so if we can integrate this curve from 0 to infinity, we will get the concentration of electrons, that is number of electrons per unit volume in this band. We will come to that in the next lecture. Okay? We've taken the density of states, multiplied that by the Fermi function to get Ne. I'll just write that explicitly. Ne is equal to GE Fe, the product. And now once we've got this distribution, as you may understand how this is coming, when we integrate this over the band, we should get then the distribution of electrons, actually the concentration within the band. So I'll stop there and we'll continue with this topic the next time. Make some calculations based on that.